Hi guys, today we will learn new Cartesian sign convention for spherical lenses. So, to give the relation between object distance, image distance, and focal length of a given lens, we need to depend on the location of these three parameters where the object is kept, where image forms, and what is the focal length of given lens. And not only that, to find magnification, the ratio of height of image to height of object, so we need to find what is the location of the height. So to find out these parameters, we are using certain sign conventions which is known as Cartesian sign conventions. So these Cartesian sign conventions we already used for the mirrors. Now I am going to use the same rules for the lens. So to get Cartesian sign conventions, first I need to draw a coordinate axis. So let me draw a coordinate axis. So this is my coordinate axis x and y. I will take the x-axis exactly on the principal axis. Now this is my positive x-axis and this is negative x-axis, and this is positive y-axis and this is negative y-axis. The first rule, so we should keep always object on left side of the lens, or we can simply write object always on negative x-axis. So we need to keep object always on negative x-axis. Suppose if I can take my object just like an arrow, so this is the object. And the second rule is we need to measure all distance from optical center. So all distances are measured from optical center. So where is optical center? Optical center is exactly at here. The mid portion of the lens is known as optical center. So we need to measure the distances always from optical center, from here to here. So this is my object distance. Object distance we are representing u. So object distance is always negative because it is always present in the negative x-axis. So that's point also you remember, object distance always negative. Now image distance, lens forms image on the other side. So if it is image, now we need to measure image distance from the optical center. So the image distance at here, if I take from the optical center, so in this case, so the image distance we were representing v, it is comes along positive x-axis. So in this case it is positive, but convex lens forms virtual image, so in that case that will becomes negative. Now if you can take that two as a two rules, the distances measured in the same direction of the incident light taken as positive. So the light ray is incidenting along in this direction. So this is the light ray which is incident on the lens along positive x-axis. So if it is a light ray is going along positive x-axis, we can take that as positive. If it is the opposite, we can take that as negative. Now we measure the distance on the negative x-axis, we will take negative. On positive x-axis we will take positive. What about height? Now here you can see the height of the object. If I draw a line which is parallel from here to there, so this is the height of the object. Now the height of the object along y-axis. So on the y-axis I can show the height from here to here. Now if this is the height we are representing along positive y-axis. Now in this case we were measuring the height from the positive y-axis. So now here the height will becomes positive. So as a rule, if you take height measures upwards perpendicular to the principal axis are taken positive. Now this height we will take as positive. Similarly, the height we are measuring from the downwards. Here you can see the image height is formed from here to there. So now the image is inverted. Now we have to measure that along with the negative y-axis. Now we can make that as a rule. The height measures downwards and perpendicular to the principal axis are taken negative. So if the height is parallel to positive x-axis, we can measure them as positive. If the inverted image forms, then automatically that height we should measure along the negative axis. So these are the rules we will keep in mind while measuring object distance and image distance and object height and image height. Now we can find the relation between object distance, image distance and focal length. So if we can write the relation between u object distance, v image distance and focal length for a lens. So we can write 1 over f equal to 1 over v minus 1 over u. So this is the relation between focal length, image distance and object distance. Similar formula we already know for the mirrors, but for the lens we will take that as 1 over f equal to 1 over v minus 1 over u. This formula we can use for the both, for the convex lens or concave lens. Same formula we can use to find the focal length of a given convex or concave lens. Now, what is the focal length of convex lens? Convex lens focal length, sine. Whether it is positive or negative. How do we find that? If we take the convex lens ray diagram, so this is the ray diagram for the convex lens. Now if you can observe convex lens ray diagram, how we define focal length? According to definition of the focal length, the light rays which converge after passing through the lens. So these light rays are converging at f2 after refraction. If I take that f2, so that f2 will be along positive x-axis. So this is positive x-axis. So if you can take that exactly at optical center coordinate axis, and if I mention this comes along the positive x-axis. Now we will measure the focal length from the optical center. And this gives positive x-axis value. So we can take the focal length of a convex lens is always positive, we will take, because after refraction those light rays are converging towards positive x-axis. So the focal length of convex lens is positive. So what about the focal length of concave lens? For concave lens, to find out the focal length of concave lens, we will observe this ray diagram. So concave lens ray diagram. So we know how to measure the focal length. So if it is concave lens ray diagram, now I'll take coordinate axis. The coordinate axis which I can take exactly at optical center. Now this is the coordinate axis, and we will measure the focal length from the optical center. So if I take the distance from the optical center to focal length. Now if you see, this point F1 is located along negative x-axis. It is located along negative x-axis. If it is negative x-axis, we will measure the focal length in terms of negative value. Therefore, focal length of concave lens is negative. So in the given problem, if we take the focal length for a convex lens is positive, for a concave lens its value is negative. So I hope you understand the focal length, how we measure. And here itself we will find magnification. So magnification we define as magnification M we defined as the ratio of height of image to height of object, or which is also equal to, for lens it is equal to image distance divided by object distance. So if you take the height ratio, image height by object height, here h dash equal to image height and h equal to object height. And in terms of distance, here image distance, we can take image distance in terms of v, which equal to image distance is v and object distance is u. So by taking any of these two ratios, either the height of the image upon height of the object or image distance upon object distance, we can find magnification. So magnification tells about how much bigger the object became. So then only we can able to find whether the image is enlarged image or magnified image or point size image. So one more concept, power of a lens. So what is really power means, how we can define that? So as a simple formula manner, we can take that power of a lens P equal to the reciprocal of focal length. P equal to 1 over F. So we are having its units also. The focal length units we are taking in terms of meter. So we can write meters inverse, or we will write that as diopters. So the reciprocal of focal length is defined as power of a lens. So power of a lens units are nothing but diopters. Now how we can define or understand it easier? What a lens can do. So if you can ask that question, suppose if I take a convex lens, so this is my convex lens. If it is principal axis, a light ray which is passing through the principal axis, parallel to principal axis, after passing through the lens, it refracts. Okay. Now, here, if we change the size of a lens, the degree of bending, means the bending of the light rays also will be changes. Okay, how much the ability to bend light rays, that defines the power. So the ability of a lens to converge or diverge light rays, it depends upon the focal length. So the reciprocal of focal length, if you can take, that we will measure in terms of power. So this power is exclusively depends upon the focal length, and the focal length depends upon the size of the lens. So as a simple definition, we define the power of a lens is defined as the reciprocal of its focal length. So if you want to make a good combination of lenses, or if you take a telescope we can use to see far away objects, distance objects. So to catch that much distance, we need high powerful telescope. Suppose if you are focusing a Jupiter from on the surface of the earth, just imagine how much far distance you have to catch. So the instrument what you are using, that should have high powerful lenses, in a simple ordinary language if we speak. So we can achieve that by keeping more than one or two lenses. If you take more than one or two lenses, so that we take as combination of lenses. So if you are combining more than one lens or two lens, suppose I am having a setup like this. So here one convex lens, and after another convex lens, and after another convex lens, three convex lenses I am having. So each one having power P1 and P2 and P3. Now these three together to me a single lens. Now if I want to calculate what is the total power, the total power I can write P equal to power total, which equal to P1 plus P2 plus P3. So we can combine the power of individual lens, then we can get the total power. So that can able to increase the ability of the instrument what we are selecting. Whenever you notice our mobile camera lens, so the mobile camera lens is having multiple lenses, more than two. So each lens having different focal length. If it is having different focal length, so it obviously have different power. So the total power we can calculate by combining the individual power of the lens. So as a simple definition, you remember the power of a lens is defined as the reciprocal of focal length. So it's P equal to 1 over F. If we can write its units are nothing but focal length units are in meters. It will gives meters inverse, which also known as diopters.